we know that we are filling the trough with water. And it's empty right now, and it starts filling up. And it starts filling up, filling up, filling up. And you see this height is a function of time. Volume is also a function of time. Okay? So my starting point has to be with the volume. That's where I have to start. Of the volume of water. This is not the volume of the trough. It's the volume of water, because this is telling us that we are filling it with water, and the volume is changed at the rate of constant rate, thank goodness, of 0.2 or 2 times 10 to the 5th cubic centimeters per minute. So now I am trying to find something to show you. I don't know, this doesn't look like a trough at all, but so I am filling this with water. So what else can I show? Can I show? Yeah, I have a cup here, but I can't turn it. Okay, so here's my cup of water, and I have water here. So I can look at the volume of water as the area of the base times the height. But I can also, and I'm not going to tilt it more than that, I can also determine the volume of the water, because this is cylindrical. That's not a good example. This is not cylindrical, but I can tilt it and say area of the base times the height. So I can say the area of the base times the height, or the area of the base times this height. So this is much easier now to see that I can put the trough on this base. So now imagine that I have this, and the trough is here. This is the base. So I can consider this the base, and this the height of water, which is 10 meters. So I can determine the water in the trough as the area of the base times this height, or the area of the base times the 10-meter height, or 1,000 centimeters height. This is how I have to construct the volume, because I cannot do it in this way. So this is my base, and this is my height, the 10. So imagine that this would be the trough, but now I'm looking at it this way. Area of the base times the height. So to make a long story short, I have to determine this area that you see here. Okay, so let's see how we do that. I'm going to enlarge this as much as I can so you can see what I'm doing. So we know that this is 80, we know that this is 20, and we know that the height is 60. Okay. So this is isosceles, meaning this length and this length are equal. So in that situation, this is also 20. And these two little pieces are equal. If 80 minus 20 is 60, then this piece must be 30, and this piece must be 30. Now, I don't know where the level, the water level is. You can say you do. No, I don't. I cannot put this in till the very end. I do not. So I will have to consider some level. I'm going to consider this level. So in other words, this is the water. This little piece here, this piece, I'm going to denote it by X. I'm going to denote this piece, this height, the tiny height, by Y. Again, what am I trying to find? I'm trying to find this area. And then I'll multiply by the height of the trough. which is 10 meters, and then I'll get the volume of water at any point in.
The height is what letter?
The height is invisible. I'm only graphing this.
No. Go back to your drawing.
Yeah, you said the height of the water.
In orange, you put an H. Is that supposed to be Y?
Yeah, it said Y. Put H.
Thank you very much. Apparently, my hand does not listen to my head. Thank you. I'm so sorry. Yes, of course. This is the height is here. Okay. So now, what am I trying to determine? This is what I'm trying to determine. The height of water at any instant, not at a particular instant, at any point in time. So this little y goes from 0 to 60. And this is a particular instant, which I do not know the height for. I denoted it by y, but it's height, but I just said we were going to denote it by y. So now I'm going to take this triangle outside. Here it is. This piece is 30. This piece is 60. This piece is the y. And this piece is the x. We had something similar before. Do you remember what we did?
Ratios?
Similar, yes, similar triangles. Small triangle is similar to big triangle. Obviously, this is a common angle. They are 90-degree angles, so they're right triangles. And this must equal this, congruent. Because they are similar, now I can write proportions with this. Again, what am I trying to determine? I'm trying to determine this area. The area of a trapezoid is big base plus small base times the height divided by 2. This is the formula. I have the small base. The small base I have. I don't have the big base. I'm trying to come up with something here. And I don't have the height. So, x divided by 30 equals y divided by 60. The other one is irrelevant because we can't use any of that. So from here, cross multiply, and I get 60x equals 30y. Simplify, of course, and then y equals 2x. Okay, so then the big base is x plus 20. So now the area of the trapezoid at any point in time. If you don't like it here, you can put it here. It doesn't matter. We still don't know where it is. So we have to look at a particular instant that is somewhere. We cannot put anything fixed in there. So the big base, x plus 20, so 2x plus 20, that was the big base. Now the small base, plus 20, and times the height in a moment, divided by 2. So that's our height. The little height is y, which is 2x. I will simplify. So the area of the trapezoid is 2x times x, 40 times x. And now I can write the volume. The volume of a trapezoid of water is the area of the base times the whole height, 1,000. That's the volume. You can distribute or not, or you can just factor out 2. So it's 2,000 x squared plus 20x. Okay, so one little thing before we start differentiating. I really want the formula to be function of y. I don't want it to be function of x. Not a problem. I'll replace it by y over 2y because I'm asked to find the age over dt. I'm not asked to find how fast is the water level changing here. I'm only asked to find how fast is the height of the water changing, not the level. So I will go back to y, replacing y in here instead of x. I lost track for a second that we were interested in the height. So y equals 2x, so x equals y over 2. So I just have to put it back. So this is the same with 2,000, and x squared will be y squared over 4, and 20 times y over 2 is 10y. I need it in terms of y, not in terms of x. I could have denoted it by age to even make it easier on us, because that's what y is. Y is age. So one more time, so y equals 2x, so x equals y over 2. When I have to square, I get y squared over 4, and then 20 times y over 2 is 10y. Okay, so now finally we can differentiate. Remember, the volume and y, which is the height, are functions of time. So dv over dt equals, oh, I forgot to ask, did you want me to use other letters, other numbers? I can use the numbers you have. I don't have any problem with that. It's kind of late now to ask. I should have asked at the beginning. It doesn't matter to me. Okay, so dv over dt. So we have 2,000 in front, and then we have 2 over 4, so it's 1/2 y dy over dt, and plus 10 dy over dt. So we are going to factor this out and then divide. Do I want to put it in? No, I don't want to put it in. dv over dt equals 2,000 1/2 y plus 10 dy over dt. And now I divide this by this. So dy over dt, that is dv over dt over all this. Now I can distribute it. So 1,000 y plus 20,000. Where, well, it was age, but it's y now, when y is, what was it? 10. And everything is in centimeters. Age or y is 10. And dv over dt is this number. Over, so this is 10,000 and 20,000. That's 30,000. Okay, so it was 10,000, yes, and 30,000. So 4 of these will go with that. So this is 20 divided by 3, and of course is in centimeters per minute. Again, I don't know how they want the answer. Oh, they want the answer in meters. I should have looked at what they wanted and just keep it in meters and change everything, but that's okay. So we can change 20 divided by 3 back into meters. So 1 meter is 100 centimeters. So 1 centimeter is 1 over 100. That's fine, meters. So then I have to go back and change it 20 divided by 3 times and divided by 300. And now this is in meters per minute. So you simplify, and 2 over 30, so it's 1 over 15. Meters per minute. So As we fill up, where is my first page? Oh, this is it. So as we fill up, at that particular instant, when the height, when this is 10, the height changes at 1/15 meters per second. Interesting problem. We cannot determine the volume of water as is. I have to determine the volume of water. I have to determine the area here and multiply by the height, as if it stands up on this side. So instead of being like this, I'm assuming that it stands like this. It's not, but just for the purpose of determining the volume. So I have to determine this area times the height. Area of the base times the height. At a particular instant. If you put the 10 centimeters in there from the beginning, you're not going to get anything. Great problem. Good. Next. Anything else?
Are we going to get a question like this on the test? To give it a possibility?
If I only want you to do that problem and nothing else.